Okay, so yeah, what's our strategy here? Remind me real quick, Kepler's third law. What's Kepler's third law say? Yeah, what's that mean though? What's T1 and T2?
The period of the orbit.
Okay, the orbit of a reference object and some other object where we're missing the parameter, right? So what about this one then? In order for a satellite to orbit the Earth 794 kilometers above its surface, it must have an orbital speed of what? Okay. So what can we do? How are we going to do this one? So this one actually isn't a Kepler's law one, is it? How could we do this? I mean, we could make Kepler's law work, but it's going to be a lot of difficulty. So let's just skip that. What do we do with this law? What's the force that's keeping the satellite in orbit?
Gravity.
Okay, what's our if it's gravity, what's the force relationship we have to use if it's gravity? We can't just use little g here, can we? Right? This isn't on the surface of the Earth. It is. It's the one that involves the 6.67 times 10 to the negative 11. It involves the capital G. So it's a universal law of gravitation, right? So universal law of gravitation says that gravitational force, which is really just ma, right? Does that make sense? Yeah, that's all the force is equal to what? What's the law of universal gravitation? What's gravitational force equal to?
The gravity constant.
So capital G
times mass of the first object.
Okay, so little m
times the mass of the second object.
Big M
divided by the radius of the
r squared. There you go. Okay, good. Make sense? Okay, so if we're looking for gravitational acceleration, then we're just going to divide each side through by m, little m, right? And so we get gravitational acceleration equals this, right? Big G, big M over r squared, okay? This is a circular orbit, though, so what kind of acceleration does that have to be?
Centripetal.
Has to be centripetal, right? So the centripetal acceleration, keeping this satellite in circular orbit, is gravitational, right? So doesn't that just mean then that we get d squared over r, because it's a centripetal acceleration, equals g m over r squared, right? And all we're trying to find is v, right? Orbital speed. You have a question there?
No.
Okay. So I'm just going to solve for v here. What do I do to solve for v?
Multiply by r.
Multiply by r. So
And then take the square root.
and then square root it. Yeah, so v equals square root of g m over r, right? We know g is a constant. We know that. What's m in this case?
5.97 times 10 to the
Okay. What's r?
6.38.
No.
794.
No.
6.38 times 10 to the 6 plus.
Okay, plus, as long as the units match up, right? Does that make sense? So r has to be, because think what we got going here. We've got the Earth, and then we've got the satellite, which is up above the Earth by a certain amount. So we've got the radius of the Earth plus the altitude of the satellite, which is 794 kilometers, right? So then all we've got to do is square root of g, which is, do you remember what g is? 6.67
Times 10 to the negative.
times 10 to the negative 11. Yeah, there you go. So g times capital M, which is 5.98 times 10, or 97 we got here, 97 times 10 to the 24. Standard units, right? We're just using standard units, divided by, what? 6.38 times 10 to the 6 plus what?
700.
No, 794 kilometers.
794.
There you go, 794,000 standard units, which are meters, right? And that's all we got to do. Okay, so we've got square root g times 5.97 e24 divided by the quantity 6.38 e to the 6 plus 794,000. Right? And what's that give us? 7,450 point blah blah blah. To three places, what's the answer?
75.
3 places.
Oh. Yeah.
7,450 meters per second. Okay. So I guess I'm not gonna want to work. That'd be the answer. Okay. That's our orbital speed, right? That makes sense. What's the key probably nugget, the concept that you really got to appeal to there? Just that, it's this one, right? That the gravitational acceleration, which we know from the universal law of gravitation, is centripetal, right? Okay. Okay, so then I wanted to show you, we made a couple assumptions yesterday, right? We said that we're going to make the assumption that big M is fixed and little m is just orbiting around it, right? In reality, that's not the case, right? And we based our understanding of Kepler's laws on that. Okay, it's isolated from other masses, right? We said if we make those assumptions, then we've got these 3 laws that Kepler gave us: the paths of the planets or ellipses, which we saw. The satellite sweeps out equal orbital areas in equal time intervals, right? And then we get Kepler's third law, which we practiced once yesterday. It just gives us a reference. It gives us a way of comparing a reference satellite to another second satellite, right? And so you can use that to solve, let's just say T1 and R1. So object 1 is the reference. Actually, object 2 would be the reference, right? Because we want to keep whatever we're solving for on top. So object 2 is the reference. Then we'd have to know either the orbital radius of the other object and solve for its period, or vice versa. You got to know one of the two, right? And this allows you to solve for the one missing piece of information, what Kepler's third law is, okay? But the question is, what happens if we don't make those assumptions? And so I'm going to we'll get to play a little bit here. I want to introduce you to something because I'd like you to try to, instead of playing like dorky video games, here's a real meaningful video game that you could play this weekend that I would encourage you to play.
Does it include physics?
Yes, this is a good one. So go to,
Is it the? Are you looking for the Fed?
I want to see, where's the, no, that's not the one I want. So we saw that yesterday, right?
Mm-hmm.
Okay, and notice the sun is completely fixed and still, and the planet is orbiting around it. And we saw a couple things like that. This is more realistic. Oops, there we go. So we want, I think this one.
That's the Fed.
Yeah, this is the one we want. I've got this one downloaded. I've got this one already in Moodle. If you go to it, there's a page where I've already embedded it. Okay, so this is pretty cool. You can do all these presets up here. So if we do a sun and a planet, for example, look what, down here it gives you, you have pretty tight control over all of the orbital parameters here. You can set the mass of the yellow body as 200, the mass of body 2 is 10. And then just imagine that this is, well, look at the position. The position is x equals 0, y equals 0. So if we superimpose the grid, right, there's the origin. We see that? These must go by hundreds. I never really looked at the grid. These must go by hundreds because look what the initial position of body 2 is. The pink body is at x equals 150, y equals 0, right? What about the initial velocities? The x and y components of the velocity of the yellow one are both 0, right? The x component is 0, but the y component is 120 for the pink one, right? So we got this thing all set up. If we show, I'll show you the traces first. If we start, look what this does. Is the sun stationary though? No, what's it doing? It's moving around. Yeah, it's moving around. Okay, so how is that? That's really important, right? Notice though that the arc is still elliptical. It's circular in this case, right? We could do some other stuff. Let's go ahead and when you're messing around with this little slider over here, notice you can slide it towards accurate or fast. If I slide this thing down to accurate, it moves more slowly. And the speed is probably going to depend on the processing power of your computer, but it's calculating the trajectory as it moves along. But it's doing more calculations to make it more accurate. It really does impact the trajectory. None of these are perfectly accurate, but this is a lot more accurate than if I speed it up. Okay, so what happens then if let's tweak something here. Let's make this, instead of 120, and you can just drag this arrow if you want to. Also, it's just hard to get it real accurate.
Give it some Y.
Like what if I did that? What if I did that and I hit start? It gives us an ellipse, right? Okay, now notice though that it still is elliptical. Kepler's laws still work. Only what's the part of Kepler's law that doesn't seem to be consistent with what we talked about yesterday?
The larger mass is moving.
The larger mass is moving, and we said that the mass of that the sun was located at one focus of the ellipse, right? So the sun is not though, right? The sun is moving around. If we tweak this thing a little bit, so let's make the masses something like, instead of making that 10, let's make it 100. Okay, and I'm going to make this, I better make this velocity a little bit bigger now. Something like that. How about?
Change that.
And now look what happens. Right? Okay, so if I ignore the yellow object, the pink satellite is still orbiting in an ellipse, right?
Yeah.
What's the difference though? What's at the focus instead of the sun? Because now this planet is half the mass of the sun, which is impossible by the way, but it could be two stars orbiting.
The average of the masses in between.
Ah, okay, yeah, it's going to be the center of mass of the system, right? The center of mass of the system. So if I pause this thing at any moment, here's a good way to think about that. If I stop this at any moment, the center of mass would be the balance point, right? So where's that going to be? Well, right between those two guys, right? That's going to be the balance point. See what I'm saying? It's going to be closer to the yellow one because it's bigger, but that's where I could balance this system if I balanced it on my pencil. If I start it again, that balance point is never going to move. Where is it now? Same place, right there.
Okay. What if you gave it x acceleration.
What if I what?
What if you give the planet significant x acceleration or velocity?
Well, I can. Let's start over again. Let's reset. So what if I just do something like that? You're saying?
Yeah.
Okay, I can do that. And I could even do this. I could even say, let's give this guy. How do I make?
Can you accelerate the sun?
Yeah, I can. I think so.
Might need to drag a
Velocity.
little bit on the outside of the circle.
I think I can give it. But if it's centered on.
Oh, yep, there it is. You hit.
Okay. Okay. Are these going to collide ever?
No.
They're not.
Can you put in another planet?
Yeah. You can
You
put
make
it
them
up to four
collide.
bodies, so you can do some pretty crazy stuff.
Can you make them collide?
Yeah. In fact, it's hard to not make them collide. That's the challenge I'm going to give you. And I messed around with this during my lunch period yesterday, and I lost all of them. I couldn't find a way to save the files, and I didn't save the settings. But this is kind of fun, because this is actually pretty realistic.
But what happens?
But what do you notice here, though? I mean, you notice that these things are always, it's that way every time. Where's the center? Right there, isn't it? Right? That's the balance point for this thing at all times. Okay? Right? So what's the big, I want to make sure everybody understands that. So this is a more sophisticated version that we're looking at of Kepler's laws. Kepler's laws just embraces simplicity, and it works fine because planets are so much smaller than stars, right? And that's what it's for. It's for very small satellites orbiting very large centers of mass. You know, a satellite orbiting the Earth. The Earth's mass is vastly larger, and so it's not a bad approximation to say that the Earth is completely at rest at the focus of the ellipse, right? One focus of the ellipse. Okay, but in reality, that's not what happens. Look what happens here. Let's pick a different preset. Let's pick sun, planet, and moon. Okay, how about this? Isn't that cool? That's really what it looks like. What's the moon doing?
Can a moon have a moon?
The moon's just circling around the...
It is. The moon is just, from the perspective of the Earth, what's happening is not very bizarre at all. The moon's just going around in a circle, right? So think what that would look like in terms of a gravity well. Okay? It's hard to visualize that, but I'll go to this one on the site. You could play this for hours. It is really fun. I mean, there's some cool stuff you can do with this. We'll come back. We'll come back to this. So now I got another challenge for you. And this isn't really mathematical physics. I just want you to build a good conceptual model of what gravity is like. So let's go to, I've got some other things. Oh, where did I put these? You'll see. We'll look at some examples where they do.
I think they just blow up.
Yeah, they just blow up, yeah. So if we do stuff like, I want to do, I think this is the one. Yeah, this is good. Okay. So this is a pretty good, do I have this thing turned on? Yeah, I do. I don't know if there's any volume on this one or not, but.
Thing that Einstein's theory of relativity predicted was black holes. And let me show you how you can explain what black holes are all about using this equipment over here. This is a 4-pound ball, which I will put in my fabric of space-time. And you can see that it curves it a certain amount over there. A heavier ball would curve it more.
It's a pretty good illustration, right?
But the point is that 4 pounds of ball curves the space like that. It doesn't matter how I get 4 pounds over there. Out here, it will still curve it the same amount. So if I were to take a different ball and crush it down, let's say make it out of lead, it still was 4 pounds, it would be a lot smaller over here, but out here, it would be exactly the same. Or if I took that other ball, ball and like really squeezed it down so it was really dense, like plutonium or something like that, it might only be this big and 4 pounds. It would pull down that cloth differently down over there. But out here, 4 pounds of pull is 4 pounds of pull. Well, supposing that I were to keep on compressing that 4 pounds, smaller and smaller and smaller, it's like a BB. You know, it's like a pinpoint. Eventually, I would get a situation where you still have that curvature, but the ball is so small that you can't even see it anymore. And that's really what the idea of a black hole is that the space-time is curved, but the mass that's curving it is so small that you can't even see it. Another way to think about it is this. Watch, if the planet rolls around up here, it goes a certain speed. If the planet rolls around down there, it's going faster. As a matter of fact, it goes faster and faster and faster and faster as you get closer and closer and closer to it. If you were to have a star, you know, you can only get so close to the 4 pounds because the star is in the way, and so it'll only go so fast. But if you don't have that star there, it'll go faster and faster, and if it goes faster than the speed of light, that's when it drops through that hole. That's when you can never get it out. And that's really what a black hole is. So the way that...
So one way to think about that, and what's really bizarre, this is all self-consistent, but one way to think about that, we haven't talked about this yet, but we're going to. I've mentioned it. But moving objects, there's some bizarre things that happen, right? Moving objects experience different relativistic effects. Moving objects get compressed along the direction of travel. It's called Lorentz contraction. They get rotated. And I'll show you guys when we start talking about relativity, special relativity in more detail, I'll show you some really good computer models of what it would make something look like. But just real briefly, like if I drove a car right down this aisle near the speed of light, you would notice that the car would be very much compressed along the direction of travel. Okay? That's one bizarre thing that happens. We've talked about how relativistic mass increases, which is why you can't push an object with mass ever to go the speed of light because its mass approaches infinity. But the other thing that happens is, clocks run slow, right? So if I were holding up a big clock as I was riding by, you would see my clock is running very slowly compared to yours when I went by. From my perspective, what am I going to see? From my perspective, I'm going to see my reference frame is at constant speed, so mine looks normal, but the world around me appears to be rushing by me at near the speed of light, and so I see the same effects. I see your clock is running slowly, and I see all these distances as being massively compressed, right? And so what's that mean? Well, when we look at gravity, gravity does something different, right? Gravity exerts the same type of effects, but gravity, notice it's warping this space. What's happening, if you look at this right here, what do you notice about if I compare the grid up here to the grid down here?
They're larger.
Yeah, it's been stretched out, right? So as you approach, what does a black hole do? A black hole just begins to stretch and stretch and stretch that more and more and more until you get to the point where the space gets so stretched out that it approaches infinity, right? And so the ironic thing about this is if you watch somebody fall into a black hole, they would never get there. Now, you would see them, their clocks would start to run more and more slowly, and you would see them just at the event horizon, but you'd never see them cross. From your perspective, they'd be there forever. Now they'd get infinitely dim. Their colors would shift towards red, and eventually there'd be so little light coming from them that you wouldn't even be able to see them. But you'd never see them cross, okay? Do they see that? No. They don't see that at all. They just accelerate and accelerate and accelerate, and they accelerate right through the event horizon, and then they're separated from the universe, and they're gone, right? But you would never see that. So one way to think about this is that space is getting so distended that you're stretching out the fabric of space so much that the distance from them to you is constantly getting stretched to the point where it gets so far that light can't keep up with that anymore, right? When the fabric of space starts to stretch faster than the speed of light, that's one model for an event horizon, because that's where the light that leaves them could never get back to you. Yes?
But what is it stretching into?
Well, it's stretching into, You tell me. I mean, it's the fabric of space is just stretching into whatever it's embedded in, right? So we can't see it. Now but see, the thing is, this is like flatland, isn't it, right? So this is what flatlanders, like this might as well be a disk taken from flatland. And so here's a gravitational center that is warped flatland. Can they see that? No, they can't see that because they're on that surface. That's their universe, right? So as they walk from here over to here, they're going to dip through that divot a little bit, right? They don't know that they're dipping through a divot. As far as they're concerned, they're walking in a straight line, right? Because they're within their flat universe. You see what I'm saying? So you can see why the idea of flatland is useful to us. Because when the question is asked, where does the divot stretches into what? Well, we can see in flatland that it's stretching into this other dimension that they don't know about. Right? All they've got is like, if this is a plane where there's the x-axis and there's the y-axis, that's all they know, right? There's no other room in their universe for another axis. It's only two-dimensional, right? For another orthogonal axis. But we can see, you silly flatlanders. There's a whole nother right angle there that you guys don't have access to. Yes?
So, how does that then affect, so like, let's just go with the flatlander concept, how does their black hole affect our dimension, and then how does our black hole?
Well, their black hole doesn't really affect our dimension. Their black hole is just a warping of their space into the extra dimension that's allowed in our universe.
So is that a black hole for them right there?
Yeah, it is. Yeah, that's a flatland black hole right there. It just goes, but what happened, you can't see the rest of it. The tube just goes down forever.
So even we can't see that?
Well, I mean, we kind of can. I mean, we could see, what would it look like? The tube just goes down and down and down. Well, we have a sense that it's going down forever down, right? They wouldn't know that. If we said it goes forever down, they'd say, huh? What do you mean? What's down? Right?
So
we don't.
Black hole is a door to the fourth dimension that we can never travel through.
I mean, not necessarily, because would you agree that a flatlander that walks down this tube is still walking on the surface, right? Still walking on this green surface, which is two-dimensional. It's just that it's so stretched out that you eventually you can get infinitely far away from, what do you mean? You can't get infinitely far, you can get very, very far away from this point right here, but where did they go? From the flatlander's perspective, or what I just
100th anniversary of Einstein's general theory of relativity. It's a little demonstration here at home to explain.
This is a really cool one, but
Another thing.
where were we?
Right about there.
Right about there.
No.
Anywhere within
No, we were at the very end,
Oh, we were pretty close.
but anywhere,
We have
anywhere
like
near
10
there.
seconds left.
Okay.
That's good enough.
All right. Well, we'll get back to this. Okay, there's another assignment up. I'll put over the weekend. I'll put one up about Kepler's laws. Short ones, but just know that they're there.
learning about the whole
Okay, mess around with the I think it's the one that's, the really good one.
Oh my God.
Mess around with that one over the weekend. The one like I did. You'll have a lot of fun with it. Just play with it. Oh yeah. Yeah, I'm testing it. You guys, yes. You got to hurry back. You guys, I have to leave you guys.
Ryan Spell, Lauren Bittwell, Edward Willard, and Travis McGee.
I'll just take my stuff and meet at tables.
Yeah.
Meet you at tables.
Okay, sounds good.
It's cool.